final international spotlight session on deep recommendations for e-commerce. And we're going to be joined by our speaker, Georges Damaskinos, machine learning engineer, Facebook, England. Well, Georges is a machine learning engineer at Facebook London, focusing on recommender systems. His research is on distributed machine learning techniques that are privacy preserving and robust against arbitrary failures such as adversarial attacks. Thank you so much, Georges, for joining us today live at the World Cloud Show. With this, the stage and screen is all yours.
Thank you for the invitation to give this presentation. Let me share my slides first. I assume that you are able to see my slides at this point.
Yes.
All right. So, yeah. Hi, I'm Georges, and today I will discuss with you about e-commerce and how we're doing things at Facebook. So, yeah. To begin with, I'm sure that many of you have been seeing the significant increase in popularity for e-commerce, largely due to the recent pandemic. From the Facebook side, e-commerce comes with the product of shops, which is for Instagram shops, and for Facebook shops, mostly available for Instagram at the moment, where you have shops of various vendors of various size, from small to big, which have some catalog and give the opportunity to the user to navigate through their products and make a purchase either on site on Facebook shops, or click on the link and go to an external website to continue shopping and fulfill the purchase. For recommendation, on this product, there are multiple surfaces, and here are some examples for these surfaces. So we have products for you. That's when a user logs on into the opens the application, and then there is a collection of products based on his past behavior or purchases, etc., that he can just scroll and observe. Then we have more from the shop, where a user has clicked and is inside a shop and is interested in some item or something, and then you have a set of items which are shown as alternatives to this one from the same shop. And then we have similar items, which is the same but from a different shop. And as you can imagine, each one of these surfaces has different goals and constraints, and we essentially have different technology behind these, like serving recommendation behind each of these surfaces, all of course related to machine learning. Now, for this presentation, let's take a step back and let's be on the same page regarding what we talk about as recommendations. And it's a very simple scheme. So we have a database of user actions and a database of items, which in our case are products, which are fed into a ranking system that outputs a ranked list of items that the users can then interact with. Typically, this list does not go beyond 20, and the users do not interact with more than top 4 or 10 items. So where does machine learning come into play, and why is it helpful and very, very relevant as of today? And to try to understand this, let's go to one of the most basic algorithms for recommendations with machine learning. This is the first thing I learned when I started my PhD, when I was did some work on recommender systems. So in a nutshell, machine learning is trying to learn to extract some information from past knowledge and use this information to extrapolate or predict on some future unseen data. So in our case of recommendations, the goal is to be able to extrapolate or predict user and item affinity. And to understand this, let's go through a very simple example. We have a database of movies, such as the IMDb database, where we have a bunch of users that rate a bunch of movies, right? And we have different ratings for different movies, user item pairs. And then we have some values -1, which indicate that this user didn't rate the particular movie, so he or she probably hasn't seen it. So our goal is to be able to make good predictions for these user item interaction. And how do we do that? So the idea of this basic scheme, which is called matrix factorization, is simple, yet it's quite close to what we actually do today. So what we do is we say we want to create a representation, a separate representation of our users and our items. So what we do is we create two matrices. One is the user matrix and one is the item matrix. So for each one of our 5 users here, denoted as rows, we have a set of 3 features. And for each one of our 5 items, we have a set of 3 features again. And the goal is that the dot product of these two matrices is as close as possible to the original rating matrix. Of course, there are some subtle important points like regularization, so we don't want it to be very, very, very close, but no time to go into details for that. So we want to create a representation that is able to give us good predictions about what we already know. So we want the dot product of these two matrices to give us this number be as close to 8 as possible. And this is where machine learning comes into play. So we use typically well-studied optimization techniques such as stochastic gradient descent, which are very, very popular for their scalability, properties and their ability to find very good local optima, like in this case. So what we do is we use these algorithms and we iteratively update these representations here, which are essentially a bunch of numbers. So we are just a bunch of floating point numbers. And we update those such that we reach a low rating prediction error, such that the output for these values is as close to the original as possible. And then at the final stage, we extrapolate. So we go to these -1 values, and then we make some prediction based on the representation that we have. And finally, we go and we get the top predictions, the top rating predictions for each user, and we give them as a recommendation. So top, I think IMDb has something like 12, no, if I'm not mistaken, recommendations for each user. And yeah, so how is this different from what is the difference with Facebook, and why can we not use this standard scheme for recommending items? So first of all, we have 3 main differences. So first of all, we don't have the luxury of having explicit ratings, and users typically interact with items through an implicit channel. Either they hover on some item, or they click, or they impress on it, and so on. So there is no explicit past history that we can clearly learn upon. The second, of course, is the scale. So there is a gazillion of users and items that the number of which is keep increasing. And the third, and also quite important, so the thing is, so in the beginning, when I started working on recommender systems, we actually started a database of movies. At that time, MovieLens was the data set to get you in, to get like the benchmark to get you going. And we did observe some temporal user dynamics. So a user behavior was changing with time, which makes sense. I mean, and as you can imagine, if this is true for the domain of movies, which is a relatively static domain, I mean, my taste in movies is not going to change tomorrow and then again the day after. You can imagine how this is a huge difference with e-commerce. So the user's behavior changes constantly here. And coming back to our picture for the recommendation, maybe a change for like a really high level change for the situation at Facebook is the following. So we have a significantly larger database for user actions and items. And for that, we need to actually prepend a retrieval system that also uses machine learning to be able to prune this set of items and feed the output to our ranking system. So we cannot use a ranking system for thousands of products. And for that, we need to have a retrieval system before that. And to give you a bit more information regarding the recommendations and how they are basically how the products are ranked at Facebook, let's go through this image here, through this high level diagram of how
also improve our
the machine learning architecture is formed. So we have that relates back to the matrix authorization basic algorithm that we discussed before. We have a set of user and item features that we store, and this can be either dense or sparse. For example, a dense feature can be the user height, and a sparse feature can be the item count string. And what we do is, again, we create representations for these data that we have, right? And this presentation is called embeddings. This is also used in the natural language processing terminology. So we create these representations, which are essentially vectors or floats, and we feed those as input to like a small, let's say, neural networks, 2 or 3 layer neural networks, which are called multi-layer perceptrons. And these networks are trying to extract a higher level representation. And what we do is we do that multiple times, and also with different embeddings from the same layer. So the final piece of architecture is fairly complicated, but the high level picture is the one I'm describing here. So that's why the model is called deep, because we stack multiple layers of these 2 components. And then in the final part at the top, we have another neural network that is responsible for actually computing the user item affinity. So the final module is giving a score indicating how much a user is likely to interact with a given item. And then we simply get we rank those scores and we get the final recommendations. So I would like to also comment on some of the bottlenecks that are there for this architecture. So for each layer, there are different bottlenecks. In the bottom layer, where we have the user data, which are the sparse and categorical features we discussed, we have a storage bottleneck, so that we have a lot of data that needs to be stored. And then when we go up one level, when we are extracting these embeddings and we want to make computations of these embeddings and therefore store them in memory, we have memory bottlenecks. And one layer upon, where we are trying to compare these embeddings with each other and see how they correlate, we have communication bottlenecks. And on the last layer, when we want to extract the scores, then we talk about basically that we have a lot of computation. So we have a computation bound workload. And as a closing thought, these are some of technologies or keywords that are very relevant to how we are tackling the challenges that I mentioned for recommendation, which is we have a scalability issue, we have implicit feedback, we have very fast changing user dynamics. So the technologies that are out there which are very relevant is distributed training on both CPUs and GPUs, parallel training, both based on data splitting and model splitting, and asynchronous and versus synchronous parameter updates. This is a bit more technical for the people who are familiar with these things. And then for the more modern architectures, such as all reduced versus more classic ones, like the parameter server, and then of course online training to be able to cater for the dynamics of the users. And with that, I would like to thank you for attending this presentation, and you can reach out at this link. Thank you very much.
Thank you so much, Georges, for that incredible presentation. We couldn't have asked for a better international keynote towards the end. Thank you once again for your valuable time.
Thank you.